Hello guys, welcome to the second part of our lecture. On the first part we discussed the joint density of states, and on this part we're going to talk about the quasi-Fermi levels and the probability of transitions. Okay, so there are some situations in which two different Fermi levels have to be defined. One associated with the conduction band. So in general we're gonna use EFC to denote this, and the other Fermi level associated with the valence band, so EFV. Okay, the V stands for valence, the C for conduction. One such situation is in the active layer of a forward bias heterostructure. So we mentioned, and we're gonna come back to this, that in the active layer, the middle layer of a double heterostructure, especially if you forward biased it, so if you apply an external potential, you will have lots of electrons in the conduction band and lots of holes in the valence band. And well, if you define only one Fermi level, let's say we're talking about a general band diagram with a conduction and a valence band, and you define only one Fermi level, let's say that it's an N-type material, so a doped material which is N-type, and the Fermi level is right here, right? The Fermi level is right here. This would mean that the Fermi function, if we were to look at the Fermi function, the probability of occupation associated with electrons would look something like this, and it would be half right at the Fermi level, and then it would go down. Right, it would keep going down in this way, and this means that the probability of occupation for for electrons is pretty large here. But this also means that if we look at the probability of occupation in the valence band, which is 1 minus f of e, let's try to look at what that would look like. This would be the area under this curve here, right? Or rather, this would be the function in this region here, and you see that it's very small. So if you have only one Fermi level, you can either have lots of electrons and few holes, or lots of holes and few electrons, or if it's exactly at at the center, you have a medium amount of both. But you could not have lots of electrons and lots of holes. So in this situation, we need to define two Fermi levels. This is an exceptional situation where we need to define two Fermi levels, one for the conduction band where you have lots of electrons, and one for the valence band where you'll have lots of holes. So again, if you forward bias the double heterostructure, the N-type semiconductor is pouring electrons in the conduction band of the active region, and the P-type material is pouring holes in the valence band. Okay, so just as a recap, you have an N-type material and a heavily doped P-type material, so both of these are heavily doped, and a lightly doped, for example, P-type material right here in the middle. Well, this means that this material has lots of holes in such a way that a diffusion current can occur. This material has lots of electrons, and if you apply a direct bias, a potential difference in this manner here, this means that there will exist an electric field here in this direction, right? If the blue side has a more positive potential than the red side, then the electric field is from the left to right here, and the electrons which are in excess here would drift against the electric field because of this electric field. So you have lots of electrons being poured into the conduction band of the active region, and because of the same electric field, the holes which are positive charges will move in the direction of the positive field. So you have lots of holes being poured by the P-type material into the active region as well. So again, that's why you have lots of electrons and lots of holes. And if the active layer has a small volume, the probability of finding holes and electrons inside can only be described by two distinct Fermi levels. Again, this is because you have in the same material, in the same region of space, lots of electrons in the conduction band and lots of holes in the valence band. If you have only one Fermi level, you could not have this. You would either have lots of electrons and few holes, or lots of holes and few electrons. Okay, so these distinct Fermi levels that are defined in these exceptional situations in the same region in space are called the quasi-Fermi level. So along with the two quasi-Fermi levels, we'll have two Fermi functions associated with each one. So, you know, with EFC you'll have the Fermi function Fc, okay, for the conduction band, and the Fermi function Fv associated with EFv in the valence band. They look exactly like the Fermi function, but the difference is the Fermi level in each one. And if we look at the picture here, so we said that, you know, when the semiconductor, or when the junction is in equilibrium, the Fermi levels align. So the Fermi level for the valence band in the active region will be the same Fermi level and have the same Fermi function as that of the p-type material here. Okay, so this is Fv, the Fermi function for the valence band. And the same thing will happen in the conduction band. So the Fermi level, the quasi-Fermi level in the active region associated with the conduction band will be aligned with the Fermi level in the n-type material. The Fv should be here, rather the Fc should be here, and the F, V should be right here, but that's it. Okay, so you have two Fermi functions. And, you know, again, this Fermi function, by looking at it, we know that there's lots of electrons in the conduction band, right? And by looking at this other one right here, we see that there are lots of holes in the valence band. And these are aligned, you know, in the valence band and in the conduction band right here. Now, to the probability of transitions, the idea here is that, similarly to the probability of occupation, a probability of transition associated with emission or absorption can be defined. Okay, so probability of a downward transition, where an electron transitions from the conduction band into the valence band and emits a photon, or the probability of transition associated with absorption, in which an electron which is down in the valence band gains energy which is supplied by a photon which is annihilated. Okay, so we have probabilities associated with these transitions as well. And the total number of emissions will be proportional to the density of pairs of states available for emission. So the joint density of states, which is we saw in the first half of this lecture, multiplied by the probability of transition, which we'll look at right now, and which will use the Fermi function in its definition. And again, an emission can occur if an electron in the conduction band recombines with a hole in the valence band. So this is illustrated right here, right? In order for an emission to occur, you need to have an electron in a level in the conduction band right here. It has to be right here, and then you also must have a hole in a lower state here in the valence band, so an empty state here. Okay, so an electron in an initial state EI and an empty state in the final level EF, so that the electron can move down and occupy this empty state, and as it loses the energy, the energy is converted into a photon. These two things need to happen in order for emission to be possible. You need to have an occupied state in the conduction band and an empty state associated with specific energies in the conduction and in the valence band. Okay, so we can define probabilities of transitions that can lead to emission, and we're going to call that F of E. And we can also define probabilities of transitions that can lead to absorptions, F of A. So F of E is the product of the probability of an electron occupying an initial state in the conduction band and a hole occupying a final state EF in the valence band. Okay, again, because as we just said, for emission to occur, you need to have an electron in an initial state in the conduction band and a hole in a final state in the valence band, so that the electron can lose energy and emit a photon. The probability that this will occur will be the probability that at the same time there will be an electron here and an empty state here. Okay, so an occupied state in the conduction band in exactly at the initial energy value, and an empty state in the valence band exactly at this final energy level here. So, and because these two things need to occur at the same time, you will have the probability of both things multiplied. So, as we've said, the Fermi function is the probability of occupation for electrons. So you need to have, so this will be the product of Fc of EI, so the probability of occupation by an electron at the energy level EI in the conduction band, multiplied by the probability of occupation by holes, which is 1 minus F of E, 1 minus the probability of occupation by electrons in the valence band associated with energy level EF. This term here is the probability of occupation by electrons in the conduction band at this energy level, and this term right here is the complement, so the probability of occupation by holes associated with the energy level EF in the valence band. Okay, so you need to have the, so the probability will be the product of these two things. And if we write these down, we have the expressions for the Fermi function. We can just substitute here. So you have Fc of EI times 1 minus Fv of EF, and this is written explicitly right here, right? So the probability of transition associated with emission is going to be, Fc of EI. So you'll see that EI is in place of the energy right here, and you have the Fermi level associated with the conduction band, and this guy right here again is 1 minus Fv of EF, which is what we're calling the final level in the valence band. So we just substituted things, and if you manipulate a little more, you end up with this, right, where you have the denominator is just the same, but if you multiply and divide this one here by this guy right here, and then you subtract the terms, you have this term here in the numerator. So e to the power of EF minus EF of EFV divided by KT. Okay, so note the difference between this lowercase f, which is the final energy level, and the EFV, which is associated with the Fermi level itself. Now you can do the same thing for absorption. So F of A is the probability of transition that will lead to absorption, and it's the product of the probability of an electron occupied an initial state which is now in the valence band, so EI dash different than EI. Okay, so EI dash now is in the valence band, EI was originally in the conduction band, and at the same time it's the product of this and also the probability of a hole occupying a final state in the conduction band, so a final energy level EF dash, which is now in the conduction band. And whereas in emission you need an electron here and an empty state here so that the electron can move down and emit a photon, in absorption you would need the opposite. So the electron would have to initially be down here, and you would need an empty state here, all right, in the conduction band. So this would be filled and this one would be empty, so that as the photon was passing by, it could be absorbed by the electron, which would gain the energy of the photon and rise to the conduction band. Does this make sense? So the probabilities are going to trade places here. So you have Fv of EI dash, okay, so the F of A is the product of the probability of there being an electron in the initial level in the valence band, so down in the valence band, multiplied by the probability of there being an empty state in the conduction band, which is 1 minus Fc of EF. Now the final level is up in the conduction band, and you need the Fermi function, therefore, in the conduction band. But this right here, so 1 minus F, is the probability that the state is empty. We usually do not say, we usually do not talk about holes in the conduction band, but this means that this is the probability that the state in the conduction band associated with energy level EF dash is empty. Okay, since you need both things, you need to have a hole in the valence band and an empty state in the conduction band. So the probability that these two things will happen at the same time is the product of both probabilities separately. So the product of the probability that there's an electron in the valence band and a empty state in the conduction band. Okay, and again we can just substitute here, and we get this. So this term right here is just Fv in the valence band of EI dash, right? Because now we're talking about absorption. So this is the probability of transition that leads to absorption, and you need an electron down here and a hole up here so that the electron can absorb energy from a photon that's passing by with energy HF. So it'll absorb the energy and move up into the conduction band. So you want the probability that there's an electron in the valence band associated with energy level EI dash, and there's a hole in the conduction band associated with energy level EF dash. Does this make sense? So this guy right here is the probability that is an electron at energy level EI dash in the valence band, and this other guy here is the probability that there is an empty state. So that's why it's 1 minus the Fermi function, and it is therefore 1 minus Fc in the conduction band of EF dash associated with this and empty, with this energy level EF dash in the conduction band. Okay, hopefully this is making sense. Now if we multiply and divide this one by the denominator here and rearrange things a little bit, we get this, where note that the term in the numerator is e to the power of EF dash minus EFC divided by KT. Okay, so one important thing to notice here is that aside from the numerator, the denominator here, if you choose the same pair of levels in the conduction and valence band, the denominator is the same. Okay, so this denominator is the same as this one right here. And this brings us to the point that in order to make lasers and LEDs, so light sources, the probability of emission in a given material or device needs to be greater than the probability of absorption. Okay, so because the material needs to emit more light or more electromagnetic energy than it's absorbing. So F of E, the probability of transitions that lead to emission need to be greater than F of A, the probability of transitions that lead to absorption. And we've just defined these two things. Now let's consider a pair of states, so one state in the conduction band and another in the valence band for both these things. So for this single pair, you can have either emission or absorption. So we'll have emission if there's an electron in the higher state in the conduction band and it moves down into the valence band emitting a photon. On the other hand, you'll have absorption if the electron is actually in the lower state and there's an empty state in the higher state so that the electron can absorb light. Okay, so and let's apply this inequality in this case. Now note that in this particular case, since we're choosing the same pair of levels, the initial energy level for emission, which we call EI, is the final energy level for absorption. Okay, so what we're saying here is the following. In this figure right here, we're illustrating the process of emission. So you have an initial energy level EI, which emission will occur if it's occupied by an electron, and a final energy level EF, which in order for emission to occur needs to be empty. But if we reverse the process and consider absorption, now this state here must be filled, so we'll look at the probability of it being filled, and the higher state needs to be empty. But we're calling now, this will be the new initial state, so it will be EI dash for absorption, and this will be the new final state, so EF dash again for absorption. And there's a correspondence, since we're choosing the same pair of states, the same pair of levels. EI for emission will be EF for absorption, and EF for emission will be EI, the initial level for absorption. Okay, that's what we're saying here. So, you know, EI is equal to EF dash, the final energy level for absorption, and the final energy level for emission is the initial energy level for absorption. So EF is equal to EI dash. And if we substitute condition associated with equation 13 and replace these expressions, so this one for f of E and this one for f of A, and again, if we substitute, you know, EI dash by EF and EF dash by EI here, the two denominators will be the same, so this one will be the same as this one. They will cancel out in the inequality, and we'll be left with this and this, where we can replace EI here, right, and leave everything in terms of the energy levels for that we have assumed for the process of emission, so EF and EI, and this will give us this. Okay, so that's where this came from. So by substituting this and this here, we get this. Now we can take the natural logarithm of both sides, and this will lead us to this. So basically EF, the final energy level for emission, minus the Fermi level EFV, has to be greater than EI minus EFC. Okay, now we just rearrange things a little bit, so let's pass this term right here to the left hand side, and we have EFC minus EFV, and pass this term here to the right hand side, and we have EI minus EF. Okay, and of course, since this is the, you know, the initial energy level EI and the final energy level EF, okay, for which in the case of emission you have an electron here which will transit down to this state associated with this energy level down here. This will be exactly the energy of the emitted photon. Okay, so HF, that's where this comes from. In the process of absorption, you have the roles will be reversed here. So initially you need to have an electron down here and an empty state right here, but this will also correspond to the energy of the absorbed photon, which will be exactly the same. Okay, so this guy right here is going to be, because of conservation of energy, is going to be H times F, the energy of the photon, either emitted or absorbed in either case. But also note that the minimum value that EI can take is EC. What we're saying here is that this initial energy level here cannot go lower than EC, which, let's remind ourselves here, is the band edge energy. Okay, because if it went lower than this, it would be in the forbidden gap, which has no states, has no levels available. So the minimum value that EI can take is EC. The maximum value that EF can take is EV. Okay, so again, the EV is the band edge energy for the valence band, so this level right here. EF cannot be higher than EV, because if it were, it would be inside the forbidden energy band. So this will be the minimum value that this can take is the EG, which is exactly, you know, EC minus EV. Okay, the band edge EC minus EV will be exactly EG, and therefore the minimum value that this can assume is EG. Okay, so this will be necessarily greater than EG. Therefore, this will necessarily be greater than EG, because if this is greater than this, which is greater than EG, then this guy right here needs to be greater than EG. And we can write this down here. Okay, therefore emission can only take place, so if this is this derived from the condition for emission, emission can only take place for, photon energies that are greater than Eg, and the condition that needs to be satisfied to make optical sources is this. Okay, so let's try to summarize here, right? Of course, in order to have emission, you need that an electron which is up here transitions down into an empty state. So the energy of the emitted photon will never be less than the gap energy right here. Okay, this has to make sense. But also, since we've derived this condition right here, what it's telling us is that the Fermi level in the conduction band, so EFC, minus the Fermi level in the valence band, EFV, needs to be greater than the gap. So if the difference between this dashed green line right here and this other dashed green line right here must be greater than Eg, the Fermi levels must be inside the band. So EFC, the Fermi level for the conduction band, must be inside the conduction band, and EFV must be inside the valence band in order to make light sources. Okay, and this sort of makes sense because if the energy level associated with the conduction band is so high that it's in the conduction band, inside the conduction band, this means that there will be a very, very large amount of electrons here. And if EFV is down in the valence band, this means that there will be a very, very large amount of holes here. And this will mean that lots of electrons can transition down and emit photons. Few electrons will absorb light because there will be, again, lots of empty states here, not electrons, and lots of electrons here, so not empty states. This is the condition that needs to be satisfied in order to make optical sources such as lasers and light-emitting diodes. Okay, guys, so this was it for our lecture today. On our next lecture, we will talk about emission and absorption rates, so we'll keep going from the point in which we've stopped right now. So, thanks very much for your attention, and I'll see you on our next lecture.